So welcome to the again good afternoon and welcome to free seminar on finite element analysis using Creo Simulate. This is Arun Karthik from the Research Engineering Private Limited. I'm working as a senior engineer CAE. So agenda of the session is about the Research Engineering Private Limited and what is Creo and what is the use of Creo and how extensive it is for design engineers and why Creo Simulate and the various spectrum of Creo Simulates, theoretical background of Creo Simulates and how it is good enough to do structural evaluation, thermal structural evaluation, kinematics and dynamics, engineering evaluations, and the session will be end up with the question and answers. So this is the profile about our company, DO Research Engineering, which is located in Bangalore, and we are the collaborative engineering services and R&D company. So we are doing end-to-end engineering simulation services. We are well experienced in FEA, CFD, multi-body dynamics, fatigue optimization, and fracture mechanics. And we have the verticals of manufacturing process simulations, thermal hydraulic simulations, electronic electrical system designs, and the corresponding simulations we are capable of. And we have the pool of experts in FEA analysis, metallurgist, material experts, tool and design experts, process development, optimization, and optimization experts, especially for topology. And it's a company established in 2010 and with the 35 engineers and 8 consultants working parallelly for engineering simulations. These are all the various tools which we are working for. CAD and machine services. We offer CAE services for FEA, CFD, multi-body dynamics, fatigue and optimization, thermal flow network simulations, chemical reactions, clean combustion developments, EMI/EMC testing, fatigue of EMI/EMC, and antenna design, PCB design, and various manufacturing process simulations of CNC, CAM, powder metallurgy, casting simulations, forging, welding, and the services we are doing with. So about PTC Creo Simulate. So everyone will be knowing about PTC. It's an extensive tool for design. Everybody will be knowing that. But in other way, Creo has the extensive and solid tool in simulation side. It was formerly called as Pro Mechanica, which was used by various big organizations like NASA and all. So they have been using for design level testing as well as some advanced level of analysis they have been using for this Creo. So we can able to do the structural evaluations, static, nonlinear, buckling, fatigue, model analysis, those kind of structural evaluations, and the thermal evaluation, steady as well as transient thermals. And it's a main good advantage of this software is it's a CAD and PLM integrated simulations. It is integrated with the CAD as well as it is integrated with the simulation. Whatever the things you are observing in the simulation, you can do the design level testing, design level verifications, variations in the designs that is in the CAD and PLM levels, and you can synchronize with Creo Simulate, and motion analysis along with kinematics and simulations. So suppose if you are doing some kinematics and dynamics analysis, you can able to bring that complicated degrees of freedom loads into the simulation environment. That is a very big boon for the software. And we are having the engineering evaluations. These engineering evaluations will be done with the software called Creo MathCAD, from which you can able to extract the equations and extract the empirical equations behind the simulations, and at last the mold flow simulations. You can able to do the mold flow simulations of injection molding, you are having the bulk of plastics modeling in plastic material along with all the thermal and all parameters which has been involved in the mold flow simulations. So PTC is a uniquely designed tool. It has all engineering terminology. It can be seamless integration with CAD and CA. And the Creo Simulate is easy to use. Yes, no FEM expert is required. In industry, R&D engineers will not be FEM expert all the time. So this tool is not required any FEM expert. Normal CAD experience is enough to use the software, and the technology is very robust. The technology is built with unique FEM approach and strong fundamentals, because the whatever the things, there is no need of separate meshing. If you want the separate meshing, if you are the mesh expert, you can do the mesh expert. That also involved with the software. So in both the cases, as a design expert, if you're not having any FEM expertise, if you're having only the CAD experience, no problem. The software is well enough to cope up with you, and the FEM approach, whatever the software is using, is unique, which was nowhere developed all the times. And the software has the evaluated against the real-time and experimental test cases. It has the cases you can see in Creo Simulate website, and that accurate it is. So whatever you are doing in the real-time experimental test is, it will be that accurate, and it's very faster, and it is intelligence to adapt the mesh functions, surface functions, curve functions, volume patches. It was very much adaptable capability it has, and the remeshing capability is very good. And we have the converge fastest. The no software has the automatic convergence. The very less tool has the option called automatic convergence. Since the software is deal with exclusive P-type element, we have the faster convergence, and it consumes very less time. And we should appreciate the PTC solution architecture, which integrate the CAD, PLM, and the CAE simulation environment, which is unique, and it reduces the time to design so it uses your design to test on various cases. And about the investment, yes, it was no like various other tools are there in CAE, like Abacus, ANSYS, and Nastran. And other tools are there. If you compare the prices affordable. And the spectrum of capabilities we have in Creo Simulate is, first of all, I would like to tell about the structural evaluations. It goes with linear, non-linear. You might be surprised that this Creo Simulate is good for non-linear. Yes, you can do material non-linearity, geometric non-linearity, boundary conditions non-linearities, and static dynamic cases like model analysis, buckling analysis, harmonic cases, spectrum response analysis, pre-stress and static model analysis can be done. This is the basic structural evaluation. Suppose if you want to do the advanced engineering capabilities like fatigue life assessments, design experiments, sensitivity analysis of a component for a particular dimensions, so design optimization. Suppose if you want to optimize the thickness of the plate, if you want to optimize the thickness of this, for example, this is the engine part, if you want to reduce the thickness, if you want to increase the ribs, so those kind of design optimizations you can able to perform. Not only in structure evaluation, thermal evaluation, in model analysis, in buckling analysis, you can able to take any measures into account, and you can control the variables with the help of the design optimization. You can achieve the optimized thickness or optimized geometry you want. So you can perform the static analysis, you can perform the model analysis for free natural frequencies, and you can get for both approaches. Even you can perform buckling in non-linear as well as linear buckling. And the fatigue life you can get with stress-based and strain-based approaches. So this is the fatigue life assessment, is an overview of that. So we have exclusive tool for PTC Creo Fatigue Advisor extension that's called this. So we have focus on crack initiations, crack tip propagations, strain life analysis. We can't see the crack tip propagations, but we can see the crack initiation point and the initial stress. You can see the crack tip stress, and strain life assessment is possible. Effective of low and high cycle fatigue is possible, and you can see the plasticity included in the fatigue formation, that is non-linear fatigue. You can go ahead, plastic collapse load, net plastic collapse load, you can able to do it by considering the plasticity by Neuber method. And mean stress correction factor with Smith-Wadsmith topper is possible. Mean stress correction factors can be included. Surface treatment like casting, rolling, polishing, those kind of finishing correction factors can be included. And biaxiality corrections like Kleiner Tippen-Crotz and Koffer-Seeger biaxiality corrections while doing the fatigue things. If you're having the experimental data, you can able to involve with it. And the extensive material property, I could say that we have unified materials and unalloyed steels, low alloy steels, titanium alloys, aluminum alloys, and you can able to include the various surface finishes like polished, machined, hot rolled, cold rolled, forged, water corroded. Those kind of correction factors can be included, and it can be replicated in the fatigue strength correction factors. And about the load histories, we have constant amplitude, peak to peak, zero to peak, then even we have the user defined amplitudes for the load histories, and variable amplitudes like load factor table and the rainflow counting is possible in fatigue life assessment extension. This is the advanced fatigue life assessment extensions, and the results, you can get the number of cycles, you can get the factor of safety, and you can see the confidence of life based on specified desired number of cycles. And you can see the post-processing of Creo. We have n number of post-processing things. You can see the fringe patterns, you can see the graph patterns, you can see the various contours, isosurfaces, it's possible. And results can be recorded, and the various measures exclusively can be taken based on some points, some surfaces or characteristics curves where we needed the specified results. And about the thermal evaluation, yes, of course, we have the linear thermal evaluation as well as non-linear thermal evaluation. You can do the steady state as well as transient thermal. You can involve the heat, you can involve the prescribed temperatures, convection, all kind of boundary condition is possible. And there is an option called, you can couple the thermal analysis with the static analysis, which is very much advanced things can be performed here. You can do the thermal dependent conduction conductivities, generalized convection properties you can involve, and the thermal load histories. For example, if you have your own defined functional thermal load histories, you can involve. If you're having a table of functional table of thermal histories, you can involve. With respect to time or with respect to any other measures, you can involve inside the thermal evaluation module. And we have the static and as well as the transient thermals. So temperature depends upon the time you can able to perform. And we have in advanced engineering capabilities, like this is the various spectrum of our advanced engineering capabilities, is a moving heat load analysis, and welding simulation is possible, lumped total heat, and coupled structure analysis. This is very important. Coupled structure analysis, what is the heat transfer, and due to the heat transfer, what is the mechanical work done. The mechanical work is replicated in the static structure mode. You can achieve that thermal load. And this is spectrum of capabilities of coupled thermal structural evaluation. As I told earlier, you can bring the thermal load into that, thermal histories into that, mechanism load into that, and your own user defined load sets can be inserted. You can see the moving the heat body. So heat input, the heat input is moving along the edges. It is possible. The welding distortion studies, design of experiments, which can also be included in thermal structural evaluations. And about motion analysis and kinematics and dynamics at the affordable price. This is the exclusive tool, and I could say it is a one and only tool available by this affordable price. You can able to do linear and non-linear motion dynamics. You can even study the position, you can even study the velocities, you can study the accelerations and the kinematics involved between your components, which is of you are having a kinematic assembly. You can perform the kinematic assembly as well as you can perform the constraint based assembly at the fraction of second. Within less time, you can get all the simulations like spring dampers, belts, gears, chains, contacts and frictions, and the frictions with varying with respect to time. So dynamic frictions, we call it as. Everything can be controlled. If you see this example as a motorbike, we are studying about the shock absorber which is placed around near to the under the seat. You can see there is a study for that. You are studying the momentum, you are studying the reaction forces, you are studying the velocities, you are studying the accelerations involved, and the damping force. There is a connection reaction force you can study in the springs. That connection reaction force and whatever the performs. For example, suppose if you're having problems with clearances and interferences at the design cycle, you can find out the clearances and interferences at the design level testing, and you can eliminate that. If you're having the if you want to import the behavior of your component with the help of Excel or as interpolation functions, you can import that into the motion analysis, and you can get that kinematics and dynamics, which will give me the spatial loads And this not only the planar loads, the spatial loads, the spatial degrees of freedoms can be transferred. The reactions, the gravity, inertial loads can be directly transferred to Creo Simulate. This is the one big good thing we can able to perform. So you can see various properties can be involved. Here the plastics is there, here the steel is there, and I have the very big stiffened component. The all other properties can be involved inside the component, involved inside the environment. And we have dynamic stress analysis, which is dynamic stress analysis, which is little advanced, and that is also possible with the help of motion analysis and motion analysis and Creo Simulate synchronizing. And this is engineering evaluations. Not only we can do the static, that is structural evaluation, thermal evaluations, and fatigue evaluations, we can also perform mold analysis. So this is the typical example of mold flow simulation. This is injection molding of it's a plastic. There are, I could say it is extensive properties available for plastic. N number of more than 200 plastic materials has been involved in the library, and you can perform the mold analysis, the MathCAD engineering design equations. We have the GT&D check, we have the tolerance analysis, we have the human factor analysis, that is we call it as Mankin analysis. The first person to interact with your model. So we are not only interacting with the model, we are seeing what is the stress going to develop with the applications, and what is the design level of optimization which is possible, and what is the mold flow. So everything you take, structural evaluations, thermal evaluations at linear and non-linear, at geometry, at contact, or any other non-linearities can be involved, or orthotrophic, anisotrophic, even anisotrophic properties can be included in the software. About the theoretical background of this tool, I'd like to tell about the difference between finite element methods. So there are two major kind of finite element approaches are there in general practice. One is H element and P element method. H element is, everybody knows that it is dividing the characteristics length, or that is the characteristics curves or surfaces or volume patches, into equal number of elements. That is the H elements. Yes, of course, this is a typical example. We have the spline over here, and the spline has been divided into equal number of meshes. So this is the linear shape function meshes. So then you can see that P element method. So this is nothing but we are increasing the order of the polynomial which we are going to use at the back end. So here what is going to do is we are not going to increase the mesh size. So you can see here the mesh size has been increased, total number of meshes has been increased, whereas in here the total number of meshes is not increased, whereas the interpolation function or shape function at the back end which we are using, the order of the polynomial has been increased to achieve the complex elements. So there is no point of error in this, and the shape function is improved and the accuracy is very much increased. The total number of mesh number is remain constant. We are not going to vary that. So we are doing the same. For example, in p-type element or H element, we are doing the convergence. But in p-type element, we are not going to increase the mesh size, whereas in H-type element, we are going to increase the meshes. In other way, we are increasing the time, calculating time, mathematics time, and this time is very important in every analysis. You could say, so you can see that PTC publishes a verification guide. If you take and check, we call it as NAFEM's benchmarks. We've compared with ANSYS and Nastron. So this tool is no more like in time, it is very less comparing to any other simulation tool. But how is it correct to mesh? We need to check. And how do you know when you have correct the mesh? For example, we cannot know in H element method, suppose the design engineer is working on the backend, he cannot know where to reduce the mesh size, where to increase the mesh size, where to maintain the aspect ratio. Those kind of steps the design engineer all the times cannot be knowing. So you need to do some outsourcing at that time specifically. But whereas here in p-type element, we are just mentioning the order of the polynomial in the software itself will correct it, and the algorithm is so strong to correct it. So it will numerically converge and achieve the display corrected mesh size. And importantly, the H element FEA solver hiding or meshing high stress constraint is good. It will exclude the, for example, if you want to exclude the high stress concentration places or stress error places. If you want to exclude those places, there is a option in the software. This is the typical example of Hutch type method. So we are increasing the elements in the first one. So we are having the 2700 elements, and you can see the accuracy of the tool, that is 466 MPa. This is the maximum one mesh stress, and we are just increasing the mesh size. That is, we are mapping the mesh size. We are doing the map to mesh and near to the characteristics curve. You can see it has been increased to 4 times, and you can see the level of changes in the stresses. And I'm increasing the stress number of elements to 12,000, and this is the corresponding stresses. And I'm increasing to 42,000. This is the corresponding stresses. So this is how the stress. This is how the mesh convergence has been happening. But the time taken is very high. You can see 0 to 2 hours it's taking. Whereas in P-type method, that I'm not going to increase anything. Directly I'm just telling the software to increase the polynomial near the characteristics curve. The software has that one algorithm behind it. So automatically it automatic adaptive technique we call it as. So automatically the meshes has been refined to the polynomials, and the time has been reduced by four times. So this is the good thing in automatic convergence. I will show you in the software. But it was the some missing points. It has one limitation and it has one backdrops. It is very less, but it is very less. As a design engineers, we don't want to consider about that. So only thing is geometric transfer and geometry healing due to translation errors. It will be neglected in P-type. That is no more required in design level of testing. It will be required in advanced level of analysis. And solve convergence secondary remesh is not there. So the software will not remesh, whereas it will do the geometry corrections. It will mesh it. It will consider the load boundary condition setup, and it will solve, and post-processing will be replicated. So this is the typical example of P-type. All the times results quality not depend on the mesh refinements always. So automatic mesh convergence, as a design engineers, you can just see the convergence over here. This is the polynomial of order 1 and the corresponding 1 mesh stress. And I'm just increasing the polynomial of order 2. Just see the level changes of, that is the stress, the results over here. So you can see the result changes, the result contours. It's a Mechanica, it's a P element technology. We have the polynomial order of 2. So 128.4 I have. Polynomial order of 3, either the mesh convergence has been taking place. P element technology is increasing the polynomial order. Usually in mesh convergence, in any CAE study, we need to increase the mesh size. We need to refine the mesh size. In other way, we need to converge the meshes before proceeding any analysis. In Creo, the software will automatically converge the analysis, any analysis before that, because we have something called P element technology. The order of polynomial will be increased, whereas the number of meshes will not be increased. You can see this example. So here, if you take this polynomial, if you take this characteristics curve, characteristic surface, the element has been increased, mapped meshes. We call it as mapped mesh. So the element near to this characteristics curves has been increased to 2,700 to 10,000, and the corresponding stress values. So similarly, I will be increasing the mesh size near to the characteristic surfaces. After that, I will be checking the maximum 1 mesh stress, and I will do the mesh convergence. This is what we call it as mesh convergence. Whereas in Creo Simulate, we have a solid technology called P elements. So that will increase the polynomial order, that will not increase the mesh size. The number of meshes will remain the same, whereas the polynomial order near to the characteristics curves, for example, characteristics curves or characteristic surface or volume patches, the polynomial order will be getting increased, whereas the number of meshes will be remain same. That's what we call it as P technology. So the mesh convergence happens. You can see the mesh convergence 140 to 141. This is the next 2 consecutive iterations, we are getting the same level of stresses. So the mesh is converged. So we are going to have some series of demos. So first, In this demo, I'm going to show you the structural evaluation. So which is of next is at the 10th Feb, I'm going to show you the thermal and thermal structure evaluations, and the 24th Feb, we'll be having N more webinars. There, in that webinar, we'll be seeing the motion evaluations, kinematics and dynamics. And at the last one, that is on March 10, we'll be seeing the engineering evaluations of design, optimization and sensitivity analysis. Those kind of stuff will be live demonstrated. Just I will show you the example. So we have two kind of installation in Creo Simulate. One is standalone installation, and it will be inside the Creo parametric. So you can buy the software as a standalone. You can use for any, suppose if you are using any CAD model packages, any other CAD model packages. If you want some simulation alone, you can get the Creo Simulate standalone. Or else if you want to purchase Creo's parametric along with the Creo Simulate, you can use the tool with Creo parametric. I'm just going to use with Creo parametric only. I'm just opening the. So this is the typical wall body. So in the applications I have is a welding. Welding is a wonderful extension model that alone will take 4 or 5 webinars to cover. So I'm not going to do that. And mold cast, this is the typical mold cast analysis, and this is what we call it as simulate. And this mold analysis for injection molding, and GD&T advisor is there. PTC MathCAD is there. Right now the license is not there for me. So I'm just going with Creo Simulate. So you can see here, so I have applied the load and constraints already. The well organized, so you can see the menus, the well organized. It's a home. You can see the structural mode, the thermal mode. If you included the thermal mode, the corresponding loads and constraints. I'm having the loads, typically all kind of loads you can take, the forces and the pressure. You can apply the pressure on the surfaces. You can apply the pressure on the imprinted surfaces, and the bearing load and the temperature structural load. You can include the load in structural evaluation as a temperature load, and the gravity you can apply, the centrifugal load, the preload. This one thing I need to tell you. I will tell in the further going sessions. And the constraints, we have displacement, we have symmetry constraints, we have the planar constraints, we have the pin constraint, we have the ball constraint, and the material, we have all materials. I will just show you. In the refined model, you can virtually draw a beam, you can virtually draw a spring with the varying stiffnesses and the excluding mass. Suppose if you want to add the extensive mass or added mass to your model, you can do that. And the shell properties can be involved, and the shell pairs can be involved. And this is what I told, the crack. The crack idealization is possible, and you can see the crack tip stress. And the interfaces, I have all kind of contacts. I have free contact, bonded contacts. You can mention the various frictions, not only static, you can include the dynamic frictions. And the weld, various kind of welded joints are there, end weld, perimeter weld, spot weld feature you can involve, and rigid links you can involve, and the weighted link at the virtual fastness. This is the surface region. Just you can imprint the surface. Suppose there is a straight surface over here, I want to imprint some surface. You can create the surface regions. You can create a volume regions. Suppose if you want to apply some material property to some volume alone, for example, I've created a volume region over here. You can apply some material to that place alone, to that volume alone. So if you want to perform the same in any of the software, for example, in any of the tool which is available in the market, it will take very long time to do, and the approach is very, you need to do some different level of idealization techniques to cut the regions, and the contacts you need to develop a lot. But here it is a very straightaway approach. And this is the editing tool, so you can even edit the CAD models. And this is what I told, if you want to do the meshing, so there is a typical meshing available. So if you want to do this meshing for the surface, possible. Just we can create the meshing for this surfaces, and we can check how it is. So this is how the surface meshes can be possible. So you can do the mapped meshing also. So we have all the controls. You can mention the element size. You can tell the edit length by curvature. For example, if you're having you can include the surfaces and you can tell the element length. So all the controls is possible, and isolate for exclusion. Suppose if you want to isolate some surfaces, isolate some volumes from meshing, you can do that. And the hard point, hard curve, prismatic elements, mapped mesh. You can do even the mapped mesh. So what kind of mesh I need to do? Quad mesh or wedge mesh or brick mesh? Any kind of mesh is possible. Not only quadrilateral or triangle elements is possible. Even you can perform the brick elements. And you can inspect as it is possible. The mesh properties, the geometry report. It is a typical mm, CAD properties. Just I will show you. I will delete the volumes which I've created already. I'm just deleting it is very easy. If you want to delete the loads, if you want to edit the loads, it is a straightaway approach. There's a constraints. I'm just deleting all. So this is the typical constraints, the displacement. I'm just going to erase this surface. So there is no need of clicking this displacement. Just select this surface. Automatically the software will ask what to do. If you want to apply the pressure, there is no need of selecting any constraint. Just select this surface and keep the mouse over there. It will ask what to do. It is like typical MS Office and all. You can just right click and see all the typical font size and font application will be there. It is as simple as it is. So you have the pressure. If you want to correct the displacement, just click the displacement. Yes. So this is the typical constraint. So this is translation constraint. I have the rotation constraint. You have three type of constraints. You have free constraints, you have fixed constraints, and prescribed constraints. Suppose this surface should move to some prescribed movements, you can do it. And with you can even set the coordinate systems with that. So I'm just giving the constraint is applied. If you want to edit, you can see that constraint has been there. You can edit that at any time. Just double click and you can edit, or else you can edit at the left side. In the left side you can see all the so you can edit over here. It is straight away. And I'm just applying the pressure to the inner surface, say some 3 MPa. I just apply the pressure. So you have selecting option. You can even select the single surface. You can select the boundary. You can select the indented surface. So we have all the features. And the materials database, we have the legacy materials, standard materials for grander design. For example, as a legacy material, we have all aluminum brands, bronze, copper, epoxies, and Fe. We have nylon, we have PVC, we have stainless steel, we have the steel, we have tungstens. I'm just selecting the steel. In the steel, we have all the options. Suppose if you want isotropic properties, if you are having the orthotrophic properties, you can include the orthotrophic properties. Even isotropic properties is possible. Transversely isotropic properties is possible. And even if you are having the advanced properties to include, you can include the advanced properties. And we have bend factor, bend table. We can tell the hardness, we can tell the hardness type, and we can tell the thermal properties. Even in thermal properties also, all isotropic, orthotrophic, and all is possible. I'm just selecting steel now. And the material assignments, we have components, we can create the volume and we can apply for the particular volumes. It is straight away approach. Suppose if you're having a composites, if you want to perform composites, the material orientation is there. You can set the material orientation. If you're having the beam, you can set the material orientation. So this is material orientation, it's possible. And the analysis and studies. So I have new static analysis, which is of typical static analysis, also included with nonlinear, linear or nonlinear. So no modal analysis. I can perform all these analysis in this software. I can perform the static modal analysis, which is used to get the natural frequencies, buckling load you can get, even you can do the nonlinear buckling. So fatigue, which can be also included with plastic properties, and I have the pre-stress. In pre-stress analysis, we can perform static as well as modal analysis. In dynamic analysis, I could say it is so good, and we can perform time, frequency, shock, and random. And you can perform standard design study, sensitivity design study, optimization design study. I'm just going with static design. So I'm giving some name. So you can see nonlinear use histories. You can include the nonlinear histories and calculate large deformation. It turns up to nonlinear analysis. It is as simple as it is. Suppose if you want to do single pass adaptive. So as it is, it will mesh if you're giving multi-pass adaptive, and that time it will increase the polynomial from 1 to 6, and you can perform it. And in output, we have stresses, rotations, reactions. Also, we can tell the software to calculate locus stress errors and the excluded elements. This is what I told. We can ignore the normalizing stress errors. We can ignore the polynomial. So if we want to limit the polynomials to 6, we can set. So 9 is a maximum. We can set the polynomial orders, and we can ignore the stresses and displacement, or else we can ignore the stresses. It's possible. And okay. So just I'm running the interactive diagnostics tool. So you can see it is a display study status. This is one good thing. So what is happening at the back end? You can see the errors, you can see the warnings, you can see the informations, you can see how it started. So how many points are there? So this is the log of it. So pass 1 is happening. So calculating element equations when it starts element. So it is that easy. The software calculates and the analysis is done. This is all the various type of results I can get. I can get the fringes, I can get the vectors, I can get the graph, I can see the model level changes. I'm just going with fringes. Fringes is nothing but the typical rainbow things. And I'm just showing with an example. See, the pressure has been applied at the center and the deformation of the wall body. Just a typical example of it. I just included the deformation pattern, deformation scale I've included. We can just switch off it. We can dynamic query, click the dynamic query, and we can check 30.0915. So it is a dynamic query include. It is straight away approach, and we can cut. We can cut. And in the dynamic we can cut and check at different places. And where is the high stress regions? Directly, if you want the high stress regions, go and click the isosurface. I'm just going with isosurface. So this is the high stress regions. So straight away you can come to conclusion these are all the places affected by the load. So these are all the places where I have very negligible stresses. So straight away you can perform that. It's a continuous tone we have, and we have various spectrum of outputs, various scales. Various views, not only the rainbow, but it has all the levels, and even you can set the level of colors. Suppose if you want, if the stress exceeds some 40, you can set the level of colors. You can increase the levels. And you can unnote it. You can write the text and we can show to the customer. And the big thing is we have the vector. Suppose I want to see the displacement in the stresses we have in various unit system. If you want in MP or in any other unit system, you can perform as a maximum principal stress, minimum principal stress. Suppose maximum principal stress. You can see the vectors, the principal stress, how it is getting varied. Just make it deform. So if you deform, what is the vectors? So the vector will also deform, and it is very easy to visualize. And display locations. Suppose if you want to in some surfaces, you can select the surfaces. Suppose if you want to select the inner surfaces, just you can see at inner surfaces alone. So the fringe pattern. So the inner surface alone. What's happening at the inner surface alone? Animate. At the inner surface alone. And you can create a measure. Maximum beam total, maximum displacement. So I have maximum displacement. Create a notion. So maximum displacement will be annotated. What are the changes you have? All. What are the changes you have? Maximum displacement will be annotated to easy visualization purposes. And we can able to normalize the stresses. That is a one big good advantages over here. That's what we call it as linearization stresses. Suppose I'm selecting the point. Select a point. So you can see the linearization is happening from point to point. From this point to this point. This is the corresponding membrane stress, bending stress, peak stress, total stress you can achieve, and you can save the reports, and even we can set the curvatures, change the curvatures and the loads. Suppose if you want the linearization of one mysis stress, if you are building some RCC MR code, so if you want to cross-check the RCC MR codes, you can perform this with the help of linearization options, and the maximum model maximum minimums is possible. And along with that you can perform the preload. You can include the preload in the volumes. So general preloads. I've deleted the second volume region. I'm just going to create a volume region over here. It is straight away very easy to create a volume region. So I have created a volume region over here. Suppose if I want to apply as preload in that volume, so this is my cross section. For example, it is some 1200, and what is the load? So preload has been applied over here, and due to that preload, so I can just do the static analysis. The name should be unique. You can do the inertial relief without any constraints. So this is with the help of typical preload. So it will take little time. See this, calculating the element equations. The total number of equations is 23,721. So each and every step it will show the run is completed. So due to the preload, what is the effect over here? The changes over here at the top. You can perform and you can check that. And even we can do the modal analysis. I'll just open another model. It's a bracket. It's an imported model. It's a step file. So I've performed the static analysis. It's running. It's a typical aircraft bracket. So it's a parallel processing. Task concurrent, two tasks is running concurrently. It is running. I'll just open the result. It is already solved. Just we can open the result alone. It's taking time, so we will go to another model. I'll just do the same in impeller. So file, new model, modal analysis, and number of modes are 10, and outputs, local stresses, mass participation factors, and the convergence is single pass adaptive. I'm just running it. So model analysis is started. We can see the natural frequencies. So past one with the elapsed time. Yes, yes, Suresh, you're right. So the analysis is completed now. So you can see the natural frequencies as mode 1, mode 2, mode 3, mode 4 and different modes is, and you can combine the modes. So the typical combination of modes, and I have so various mode shape changes and the stresses, all the typical stresses. It's a typical von Mises stress due to this mode, and you can see the stress contours over here. We will come to this question and answer session, 5 minutes. I'm having the displacements of magnitudes, various magnitudes I have. And this is a typical fatigue. You can perform the fatigue analysis. We can just include so we can just include the yield stress. We can tell what is the fatigue uniform law, and we can this is the different fatigue criterion I have, the distortion energy theory, uniform material law. I'm just mentioning the and we can perform the fatigue analysis. It's a straightaway stress approach. So we can use the static analysis, and we can tell the endurance limit, and we can tell the various amplitude type peak to peak, and what is the load sets, constant amplitude or variable amplitudes. Variable amplitude it's possible, and we can even calculate the factor of safety. Okay. So fatigue analysis is running at the back end. So you can see fatigue preferences, log file, desirable life units. There's a metadata. So desirable life is 1 e power 5, 1 e power 7. Biaxiality correction is on. Confidence level is 90%, and the mean stress method is Moro method. And we can check the log and checkpoints and the log. So when the model error checking starts, when the checking the model after creating the elements. So these are all the various logs. So it's running at the back end. Let it run. So in the same way you can perform buckling analysis. You can get the buckling load. You can get the pre-stress. We can get the dynamic and all analysis we can perform at the same time. We can synchronize with static analysis. We can synchronize with nonlinear analysis. Suppose if you want to perform buckling analysis with nonlinear buckling, you can just do the nonlinear static analysis. Then we can perform the nonlinear buckling analysis. Just the buckling analysis we can perform. So since the time exceeds, I'm just coming to the question and answer session. So fatigue analysis is running. Any questions from attendees? I'm just making you all unmute. So please ask your questions. So I forgot to tell that one more thing I forgot to tell is various connections and crack we can insert. We can insert the crack and we can perform the static analysis. If time permits, I will show you that. Any questions from attendees? Any questions from attendees? Fatigue life is done. So this has a constant fatigue life, and I have the log damage and I have the factor of safety. So factor of safety is very less over here. So this we can take it as a hotspots. Factor of safety is 5 over here. And I have the confidence of life. So confidence of life is good. So this plain green indicates that confidence of life is good. So finally I would like to show you how the crack has been inserted. I'm just going to the modeling. I'm just inserting a crack, a sketch, a typical circle, I'm just creating the plane over here. Done. Sketch, and I'm inserting a crack over here. And fill this so it's already a surface, and I'm just telling it as a crack. So crack has been inserted. Just performing the statics once again. So there is no need of meshing. I haven't did any meshing at the back end. So attendees, please put your questions in the chats. As you can see that crack has been started. Analyzing. Yes. So there is a crack over here. And this is the crack tip opening. And the crack tip stresses. We can also include the crack over here and we can check. And straight away we can do the design optimizations. We can minimize the maximum bending or maximum deflection or maximum one mesh stress. Suppose we can tell the maximum one mesh stress, and we can include the dimensions to optimize the study, and we can run the study. So this is the optimization study, we can run it. These things we will show later on. And we can create a new measures, any measure over model or over selected idealization or over composites of our layers we can select. And we can set the model setup. 2D plane strain, 2D planar strain, 2D axis symmetric, it is possible. And we can perform the beam 1D problems. So all one-dimensional, two-dimensional and three-dimensional is possible. So any cases, if you want to contact us just for Creo Simulate to do FEM, MDB or optimization solutions, just contact us. So sorry, the initial has been wrongly typed. This is Arun Karthik T. So this is my mail ID, and you can call us by this below number. any benchmark, and we can do the trainings, demos to the team as well as individuals. Thanks for attending. Once again, I thank all of you for attending the free webinar on finite element analysis using Creo Simulate. So we will meet in the next session. Hopefully, we'll meet in the next webinar for thermal and thermal structure evaluation. Thanks to you.